All right, so here we have this truck that's in a circular path, right? It's going around a flat curve. So if you're driving your car and you turn around a curve, that's basically a circular path, right? So the best place to put yourself when you're thinking about this problem is directly in front of the vehicle, as if the truck is about to run you over, okay? Because then you're going to see all the important forces. So standing directly in front of the truck as it's coming at you, what are the forces you would see? You're standing in the road, the car is coming around the curve, here it comes. What are the forces that you see? Normal force, the truck's on a surface, so there's a normal force. So Fn is up, mg is down, it's supposed to be straight down. All right, and then there's one more. Friction. So here's the center of the circle, let's say. So over here represents the center of the circular path. There is a frictional force pointing to the center, and it's actually static friction. If we looked at the car from the side, because look, here's where kids get confused. So let's say you're looking at the car from the side, like as it drives past you, you would see mg down, normal force up, and friction back, but that friction's different. That's a kinetic friction. Does that make sense? There'd be a kinetic friction pointing behind the car. We don't care about the kinetic friction. The friction we care about is the static friction that points to the middle. Now, why would this be a static friction? Well, look, is the car moving in this direction? Is there any side-to-side motion? No, so it would be a static friction. Okay, we don't care about the kinetic friction here. So static friction equals mu static times normal force. Okay, for circular motion problems, always make the center of the circle positive. Okay, so now what we do is we sum the forces. Sum the forces x, sum the forces y. So in the x direction, the only force is the static friction. So this is mu static times the normal force. Any other x forces? Nope. So what is the sum of the forces equal to? ma, but that's a centripetal, right? Because it's in a circular path. What is centripetal acceleration equal to? It's equal to v squared over r. So we can just plug that in right there for centripetal. So this becomes m v squared over r. And there is a very useful equation for this situation. All right, in the y direction, we have normal force up, mg down. Sum of the forces equals ma. But is there any acceleration this way? Centripetal or linear? Nope. So that goes to 0. This crosses to 0. So normal force minus mg, this whole thing is just 0. So now, how do we go about solving this problem? Well, first of all, what's normal force going to be? mg. Solve that for normal force. Normal force equals mg. Plug it in right there. So now I'm going to rewrite this first equation right here, this x equation. So rewriting that equation, we're going to have mu mg equals m v squared over r. So the m's cancel, the m's drop out, and we're left with mu. I'm going to solve this for mu g. So mu g is going to be equal to v squared over r. Now look, this problem gives us two situations. The first situation is the truck traveling at 32 meters per second, and then the radius of the curve is 150 meters. The second situation, the truck is going around a tighter curve, right? It's not as big of a radius, so it's going to be like a sharper turn. The question is, if the truck can go 32 meters per second, when the radius of the curve is 150, how fast can the truck go if the radius of the curve is 75 meters? So look, what stays constant from situation 1 to situation 2? So here's the equation I've derived so far. What stays constant from situation 1 to situation 2? Is the coefficient going to change? No, dude. The coefficient is it's a measurement between the tires and the road. You know, I mean, if situation 2 were suddenly on ice, then that would change the coefficient. But the road's the same, the tire's the same, so the coefficient is constant. And how about gravity? Gravity is also constant. So look, what you could do here is you could solve for mu. You could solve this, use situation 1, figure out what mu is. Then go to situation 2 and calculate velocity. But here's what I would do. If this is constant, if mu g is constant, then what must be true about this? It's also constant. So I would say this. V1 squared over R1 is equal to V2 squared over R2. Did everybody see what I did? Because look, mu g, this is constant, so that means V squared over R must be constant. What are we looking for in this equation? We're looking for what? V2. So V2, when you do the algebra, is going to equal V1 times square root of R2 over R1. Like that. Okay, I need some room. So taking that, so picking up from right here. So V2 equals V1 square root R2 over R1, so you plug in. So V1 was 32 meter per second, R2 is 75 meters, R1 was 150 meters, so this gives 22.6. Okay, that's how I did it. Look, probably most students would prefer taking this equation. If you're like, what the heck did you do, Spaldo? Some kids get this, some kids don't. Another way you could have done it, just figure out what mu is. Find what the coefficient is for situation 1, and then plug that coefficient into situation 2 and solve for the velocity.